All right, so we are recording. Let me get up my little spotlight here. There we go. All right, so welcome to our last class. You've done it. You've gotten through Chem 2 in a very abbreviated summer semester. So kudos to you for getting that all done. So a couple of reminders of due dates in the next couple of days. You do have a lab with a due date of tomorrow at 11:59 on redox reactions. And then on Monday, you have the last set of homework, which is on electrochemistry, and a lab on electrochemical cells. And if you choose, there's an extra credit lab there as well. I did talk about how if you get the redox reaction and the electrochemical cells and the extra credit lab all done by tonight at 11:59, I will add 10 additional points to your lowest quiz score. And if that's really a crunch for you, I will add 5 extra credit points if you can have all the labs done by Sunday at 11:59. And again, if that's not something that you can do, that's fine. Really, the redox lab is not due until tomorrow night. And then the electrochemical cells and the extra credit lab have a due date of Monday, since Monday is the last day of class. But you do have a couple of extra options there for some extra points to add on to tests if you've been kind of keeping up with all of your work, and you can get some stuff done in advance. The final exam is on Monday as well. And it is 2 parts. Part 1 is going to be 60% of the exam. And that's essentially a test on chapter 15 and 16. So KSP was chapter 15 and electrochem was on chapter 16. And it will be, where you need to show all your work, and then you're going to be submitting that work when you're all done. And then the second part of the final exam is 40%, and that's really the cumulative part on all the other stuff that we went through throughout the semester. So let's switch to the document camera here and go over our warm-up. Actually, let's just look at the warm-up first. So for the first question, okay, we're trying to calculate the cell potential for this particular cell. Now, the important thing to notice about it is that the concentration of cobalt ions in this cell is 0.50, and the concentration of copper is 0.25. That means this is not a standard cell, because standard cells have 1 molar concentrations. And if there were gases, the gases would be at 1 atm. This doesn't have gases in it, but so it's a non-standard cell. So what we would do, the cobalt is going from a 0 to a +2. Okay, that means that it is losing electrons or it's being oxidized, and oxidation takes place in the anode compartment. And we can look that reaction up on the table. It actually would be written, sorry, would actually be written as a reduction, doesn't matter. And the value is negative 0.25. Sorry. The copper ions are going from a +2 to a 0. So they're being reduced. Reduction takes place in the cathode compartment. Sorry, I have a tickle in my throat. And when we look up copper ions being reduced on a reduction potential table, that value is 0.34. So the first thing we're going to do is we're going to calculate what the voltage would be across that cell if it were at standard conditions. And the way we do that is by taking the value at the cathode and subtracting the value at the anode. So we would take 0.34 and subtract negative 0.25. Since we're not at standard conditions, the next thing we would do is calculate Q. So we would take the concentration of the products and divide it by the concentration of the reactants, and that would give us Q. And then we can plug in the voltage at standard conditions here. And then take negative 0.0592 divided by n times the log of Q. And together, that's going to give us the voltage for this non-standard cell. N is the number of electrons. And since we're going from a 0 to a +2, we have 2 electrons being lost here. And since we're going from a +2 to a 0, we have 2 electrons here. So N would equal 2. When we look at the second problem, okay, this is an electrolysis problem or an electroplating problem. So we're going to take the current and we're going to multiply it by the time to figure out our coulombs of charge. And then we can use Faraday's constant to figure out how many moles of electrons that's equal to. And then we can take the moles of electrons to find out the moles of copper, and then use the periodic table to come up with the grams of copper, or the mass of copper that was plated out during that time period. So those are our thought processes. Let's switch over to our document camera and see how you did. All right, so for the first one, okay, and I wrote out a little bit more work than you necessarily needed to, but remember that we put the oxidation first, so copper atoms are going to copper ions, and we put the reduction second in our cell notation, so copper ions to copper atoms. The values were given to us in the context of the question, and if we were looking at a standard cell, we would take 0.34 and subtract negative 0.28. And that gives us positive 0.6 or 2 for the voltage. And again, that would be if this were a standard cell where the concentration of the ions are 1 molar, they're not 1 molar. So we have to go a little bit further. To calculate Q, we would take the products over the reactants. Now, what I did is I just took the cell notation and I wrote it out as a chemical equation. You don't necessarily have to do this, but the copper or the cobalt atoms are going to cobalt ions. So cobalt atoms are on the reactant side, cobalt ions are on the product side. And the copper ions are going to copper atoms. So I've got copper ions going to copper atoms on my product side. So that means that the cobalt ions are my product and the copper ions are my reactant. So I would take the concentration of my product, which is the 0.50, divided by the concentration of my reactant, which is 0.25, Q equals 2. So now I can use my Nernst equation to calculate the voltage across this non-standard cell. I would substitute in the voltage if it were a standard cell. So I'm going to substitute in 0.62 here. And then I'm going to subtract 0.0592. This is a constant divided by n, where n is the number of electrons. And we have 2 electrons that are being lost in our oxidation and 2 electrons that are being gained in our reduction. So n equals 2. And then we'll take the log of 2, plug that in, and the voltage is a little bit less than if it were non-standard, or than if it were standard. So the voltage would be 0.61 instead of 0.62. Now, there is another equation that you could use that just uses the natural log function in the equation, and then it just changes a little bit what that constant is in the equation. It gives you the same answer either way. But again, the idea behind this is that we're looking at a non-standard cell. We're going to use the Nernst equation to calculate what the voltage is across that cell. So questions on that first review question?
Yeah, no, so for the anode, we were given negative 0.25.
Oh, you were?
Yeah, at least what it says on the warm-up.
It could have been. I could have written down the wrong number. Sorry. Man, I really have something in my throat. This should be 0.25.
Yeah, that was what's on the warm-up
right.
page.
That just means I wrote it down too fast. So 0.34 plus 0.25. Oh my God. So that makes this 0.59. Probably won't change. Oh my God. Hold on a second. Oh, clearly I have something that got stuck in my throat. So that would just change this number here, right? So this should be 0.59. So negative log of 0.0592 divided by 2 times the log of 2. Oh, that's all right. You'll get 0.58 for an answer. Do we agree with that?
Why is 2 put in place for n in the
Okay, so
equation?
N is the number of electrons. So when we look, when copper or the cobalt atoms become cobalt ions, they're losing 2 electrons. And when the copper ions become copper atoms, they're gaining 2 electrons. So N equals the number of electrons in that balanced equation.
Oh, okay. So it's not 0?
No, it's not 0, it's 2.
Oh,
So
okay.
you've got 2 electrons, 2 electrons. So N is going to equal, I think in the problem we did the other day, N was equal to 6. It's just the number of electrons in that balanced equation. And it's a coincidence that this number here and this number here are the same. They don't have to be. They're 2 different things. This is the number of electrons. This is the value for Q for that non-standard cell. They just happen to both be 2 for this question. All right, and we have something in the chat here too. Yeah, I have some water. I'm trying to, whatever it was, I ate my dinner real fast and obviously I got something caught in my throat. I'm better though, thank you. All right, so we okay now? Sorry about that transposition of a wrong number there. All right, so let's take a look at the second question. Okay, so for the second question, we do have to know how many electrons are involved in the electrolysis process. And we have copper ions in the solution, and they're plating out as copper atoms on, whatever we're plating them on. So this is going to be a -2 charge. So to figure out the charge first, we would take the current, which is 2.0 amps, and multiply it by the time, which is 45 minutes. An amp really is, and it doesn't really matter if we write that way. An amp really equals 1 coulomb per 1 second. It's kind of a shorthand for 1 coulomb per second. So this is really 2.0 coulombs per second. And if we want to cancel out the time, we have to get it in seconds. So we would take 45 minutes, 1 minute equals 60 seconds. So this becomes seconds, multiply it by your current, and that's going to give you your charge. So 5,400 coulombs of charge are passing into that electrolysis cell during that time period. What can we do with that? Well, we're going to take the coulombs of charge and multiply it by Faraday's constant. Faraday's constant tells us how many coulombs there are per mole of electrons. So, and it's a constant. So it's 9.65 times 10 to the 4 coulombs equals 1 mole of electrons. So we've converted from coulombs to moles of electrons. Up here, for every 2 moles of electrons, we're producing 1 mole of copper. So we're going to go from moles of electrons to moles of copper using that ratio. And then once we're at moles of copper, we can go from moles of copper to grams of copper by just using the atomic mass off the periodic table. So if we have 2.0 amps that runs for 45 minutes through this electrolysis cell, 1.8 grams of copper would be plated out onto our cathode. Okay, so what kinds of questions do we have with that? It's similar to, I think, the last problem we did on Tuesday. It's just a different metal and the numbers are different, but the idea is the same. All good? All right, so let's go back. All right, so we did all of that. Let's talk a little bit about your final exam on Monday. It will be open the same time period that your tests have been open throughout the semester. So I will have it open at 11 o'clock on Monday, and it will close at 8 o'clock on Monday. And I'm not going to make accommodations for other times because we have class scheduled from 6 to 8. So at the very least, you should be available from 6 to 8. But I'm giving you a much larger window in case that's a little bit helpful to you. And again, there's going to be two parts. One part will be an actual cumulative final exam on all of the information except for the most current information. And then we'll have a part that will be on the most current information that we didn't have a test on yet. So to look at this, 11 to 8, yep. So for the cumulative part, there will be 6 questions and you'll have 45 minutes. They will be ones that you have to do work on and then submit your work when you're done. So that's why there's just 6 questions there. So we talked a lot about concentrations for solutions. So knowing how to calculate molarity and mass percent and molality. And maybe you're given the molality and you want to calculate the molarity, or you're given the molarity, and you want to calculate the mass percent, something along those lines. We talked about enthalpy and entropy and free energy. So enthalpy is delta H, and that is whether something's exothermic or endothermic. Okay, so if it's a negative delta H, it's exothermic. If it's a positive delta H, it's endothermic. Okay, entropy deals with the disorder in the system. That's your delta S value. And if you increase the disorder in the system, if things become more random, then delta S is positive. And if it becomes more ordered, then delta S would be negative. And free energy is dealing with spontaneity. So if delta G is negative, a process is spontaneous. If it's positive, it's non-spontaneous. Okay, maybe you're given the information for delta H and delta S and delta G, and you can use the sum of the products minus the sum of the reactants to find out the value for a reaction. Or maybe you're given the enthalpy and the entropy, and you need to calculate the free energy, and that would be your delta G equals delta H minus T delta S. Okay, things like that. Kinetics, rate laws. We talked about rate laws and integrated rate laws, where rate laws deal with how concentration changes affect rates of reaction. And integrated rate law was how concentrations affect the time of a reaction. Kind of basic equilibrium problems, okay, calculating K, or maybe calculating Q and deciding whether a set of conditions is at equilibrium, comparing Q to K. And if maybe a system is not at equilibrium, which way would it shift to establish equilibrium? And then some specific equilibria with respect to acids. So maybe calculating the pH of a weak acid, or calculating the pH of a weak base. It's just a specific type of equilibrium problem. Buffers, where you have a conjugate acid-base pair in a solution, and how you can use the Henderson-Hasselbalch equation. I just wrote HH instead of typing that a lot, to calculate the pH of that buffer solution. Or maybe adding an acid or a base to a buffer solution, and how does that affect the pH? And titration, so taking a strong acid and a strong base, or a strong acid and a weak base, or a strong base and a weak acid, and calculating what the pH would be at various points during the titration. And we just worked with weak acids and bases and buffers and titrations. So probably we will not spend a whole lot of time reviewing that kind of stuff today, since that's the most recent stuff. We'll go back and look at stuff that's not recent, I guess, in your memory. And then for part 2, there will be 9 questions and 75 minutes for that. And that's on chapter 15, which is KSP, and chapter 16, which is on electrochemistry. So knowing things like if you are given concentrations of a saturated solution, what's the KSP value? Or if you're given the KSP value, what are the concentrations in the saturated solution? Or maybe adding a common ion to a saturated solution, and how does that affect the concentration? For the electrochem, identifying what's being oxidized or reduced, or what's the oxidizing agent or the reducing agent, balancing redox reactions, okay? Calculating the voltage across either a standard cell or a non-standard cell. Calculating either delta G from your voltage or your voltage from delta G, and then electrolysis. Okay, so those kinds of things are going to be on your final exam. And I did email this to you on Monday or Tuesday, so hopefully you got a chance to look at that and kind of absorb the things you're going to be looking at. So before we go on to some more review questions, I do have an answer to a question that I think Alex asked before, and I do apologize for this. There is a mistake in the syllabus that was not changed. The extra credit lab, if you get a 90 or above, is not replacing your lowest test grade, but it is giving you, I think, 15 points. Let me double check. Yeah, it gives you 15 points on your lowest quiz grade. I'm not sure exactly where that replacing must have come from, an old syllabus that somebody put together. So I apologize for that. So that answers that question. All right. So let's
I had a question about part 1. For part 1, is it all calculations, or is
everything is yes, everything is calculations on this,
okay.
This final. Yep.
Okay, and there's no conceptual.
Yep.
Okay.
So actually, that's a good question. So that in that way, it will be different than the rest of your tests, and that part 1 is not going to be, I guess, more the conceptual, like you said.
Okay,
yeah.
thank you.
Yep. And then there'll be a place for you to upload your work for part 1, and there'll be a place for you to upload your work for part 2. Okay, good question. Thank you. All right, so let's just spend a couple more minutes on electrochemistry. And then we'll go back, we'll look at a couple of KSP problems, since that will be on our final exam, and then we'll do some older material. So for this question, okay, it says, how long must a current of 5.00 amps be applied to a solution of silver nitrate to produce or to plate out 10.5 grams of metal? Well, silver atoms are formed by +1 ions gaining electrons. So it's going to be a 1-to-1 ratio of moles of silver ions to moles of electrons. And Faraday's constant is going to enable us to go from moles of electrons to our charge. And if we know our charge and we know the current, we can calculate the time. So in a way, we're kind of working the problem backwards of the way we did it in our warm-up. In our warm-up, we figured out how much metal was plated out. In this one, it gives that part to us. So we start with 10.5 grams of silver. We can use the periodic table to convert from grams of silver to moles of silver. Since silver forms ions with a +1 charge, we know that from the silver nitrate solution that we're using. It's a 1-to-1 ratio of moles of silver ions to moles of electrons. And then Faraday's constant enables us to convert from moles of electrons to coulombs of charge. So if 10.5 grams of silver was plated out, 9.39 times 10 to the third coulombs of charge flowed through this electrolysis cell. We don't want to know the charge, we want to know the time. And we looked at our equation here that relates charge, current, and time. So Q equals I times T, where Q is the charge, I is the current, T is the time. When it says how long, it's asking for time. So we would divide both sides by our current and we can calculate the time. So our charge is 9.39 times 10 to the 3. We're going to divide it by 5.00 amps. Now, again, an amp is really a coulomb per second. So coulombs cancel out, and we're going to get our time in terms of seconds. And we get 1.88 times 10 to the third seconds. That's a really large number of seconds. If we divide that by 60, that would give us minutes. It didn't really designate the time you needed, so you could have left it in seconds, but you know, it's probably better to say your time is 31.3 minutes as opposed to, you know, whatever that is, 800 or 1880 seconds. Just a little bit better. Everybody okay with that? It's essentially backwards of what we did before. Okay, and the question we had before, we knew the current and we knew the time and we calculated the charge. And then we took the charge to find out the moles of electrons, to find out the moles of atoms, to find out the grams of atoms. This time we're just working the problem in the reverse direction. All right. So let's do a couple of KSP review problems, because again, KSP and electrochemistry are going to be on one part of your final exam. So in this case, we have calcium fluoride, and we're told that the KSP for calcium fluoride is 3.9 times 10 to the minus 11. We want to calculate the molar solubility. So as a review, since this was in the last chapter, you want to write down the dissociation of this slightly soluble salt first. Break it up into its ions. Then you want to write your KSP expression, same as every K expression. So your products over your reactants raised to the power of the coefficient in the balanced equation. Your product or your reactants are always solid, so they don't get included. Substitute in 3.9 times 10 to the minus 11 for KSP, and essentially you're solving for X in your KSP expression. That'll give you the molar solubility. It'll tell you what the concentration of that saturated solution is. Now, after you do that, we're going to change the problem slightly. Okay, in the second question, it's the same salt, so it's still a calcium fluoride, and the dissociation is the same, and the KSP is the same, except that we're going to be getting calcium ions not only from the calcium fluoride, but also from the calcium nitrate. So the second problem that's here is a common ion effect problem, where you're getting calcium not only from the slightly soluble salt, but also from another source. And see how that changes your molar solubility. Okay, and when you get, let's say, when you get the second X value, when you get the second molar solubility, put it in the chat so that I know time-wise we can switch our camera over and see how we do. If you're not sure what to do, this is like a working session. So, ask any questions that you want as we're going along so that, you are really clear on what you need to know for when you do this on your test. Bless you, I think. All right, to make sure you have all the information down, and I will switch to my document camera and we can take a look at the first part. And then look at that second part.
Is your phone or using it? Or you're charging it?
Good, excellent. All right, so let's see. All right, so we got a couple of answers for the first parts. Let's see how we did. Okay, so we're taking calcium fluoride. We're breaking it up into calcium ions and fluoride ions. KSP is just a specific type of equilibrium. So it's products over reactants raised to the power of the coefficient in the balanced equation. Remember, we don't include solids. So when we write KSPs, it's the concentration of the cation times the concentration of the anion raised to the power of the coefficient in the balanced equation. So we've got the concentration of calcium to the 1 power, which I'm not going to write, times the concentration of the fluoride ion squared. So there's our KSP expression. Now, KSP problems are either you're given the KSP and you're trying to calculate the concentrations, or you're given the concentrations and you're trying to calculate the KSP. So in this case, we're given KSP. So 3.9 times 10 to the minus 11 gets substituted in here. We don't know the calcium ion concentration and we don't know the fluoride ion concentration, but we do know they're in a 1:2 ratio. So for calcium, we're going to plug in X. And for fluoride, we're going to plug in 2X. And we have to square it. So this 2 here and this 2 here comes from this 2. So we're doubling the concentration relative to the calcium, and we're squaring it based on the KSP expression. So 2x squared that gives us 4x squared, times x gives us 4x cubed. So we're going to divide both sides by 4 and then take the cubed root, and that'll give us our concentration. So 2.1 times 10 to the minus 4 is the molar solubility. It's the molarity of the calcium fluoride in this saturated solution. Now, it's also the concentration of calcium ions in the solution, because that's X. And if we were to double X, that would give us the fluoride ion concentration. But the question just wanted to know, what's the molar solubility for calcium fluoride? And that's what X equals. Good, excellent. Now, let's look at the second problem. It's the same KSP expression, but the difference is, for the calcium ion, we're getting X amount of calcium ion from our calcium fluoride, but we're getting 0.010 from the calcium nitrate. This is a common ion effect problem. And because our KSP is so small, the amount of calcium that we're getting from the calcium fluoride, this X value here, is insignificant. So we can change this to just be 0.010. And we're taking 2x squared, that gives us 4x squared, multiplied by 0.010, so that gives us 0.040x squared. Divide both sides by 0.04, that gives us x squared. Take the square root of both sides, and that gives us our molarity. Now, let's take a look at what that actually means, okay? And we'll kind of draw in another thing we talked about. So if we've got calcium fluoride and we dissolve it in water, it's going to break up into ions, okay? It's an electrolyte. When we have a saturated solution, the rate of dissolving of that solid will equal the rate of precipitating of the ions, and we have a saturated solution. Now, in the first problem we did, we were just calculating what the concentration of the calcium fluoride was in that saturated solution. In the second problem, we increased the concentration of calcium ions because we added a common ion to it. So think back to Le Chatelier's principle, okay? If we were to increase the concentration of calcium ions, which way is this equilibrium going to shift? Is it going to shift to the left, or is it going to shift to the right? Okay, so if we increase a product, the equilibrium is going to shift in the other direction to use up some of what we added. So it's going to shift to the left. Okay, now, we had one other thing I wanted to. Where can you find the charges on the individual ions again? Okay, so there's a couple things that you can do. Really, they come off the period. Actually, let's just do it this way. They come off the periodic table. Okay. Calcium is in the first group on the period, or sorry, second group. It's an alkaline earth metal. So that means it's got a +2 charge. And fluoride is a halogen. It's in group 7. So that means it's a -1 charge. What you also could do, and this works for almost all the time, this 1 came from the charge on the fluoride, and this 2 came from the charge on the calcium. So you kind of do almost like a reverse crisscross to figure out what the charges are. They will always start out in KSP problems. You're always starting with a solid, and you're breaking that solid up into its ions as it dissolves because it's an electrolyte. So it's the way that the question will always be set up. Okay. So we kind of reviewed KSP, and we also reviewed common ion effect. Anybody have any questions on those? All right, my friends. So let's look at another question. Oops. All right. And again, this time is more for you than anything else. So if you have questions, as we're doing, these problems or something else comes up, now's your time to ask them. Okay. Oh, and you said, will we need to perform calculations on common ions? I'm not sure what you mean. You like that second question we did, like this? You could see a common ion problem. Yep. Yep. All right. So let's try another one. This is another type of KSP problem. Okay. In this case, we have 0.10 moles of potassium X, whatever X might be, doesn't really matter. And we have 0.10 moles of potassium Y, whatever Y is, okay? And we're going to add silver nitrate gradually to our KX solution and gradually to our KY solution. And we want to decide which one will start to precipitate first. So we're given the KSP for AGX, and we're given the KSP for AGY, and we want to decide which one is going to precipitate first. So what you want to do, this is kind of a common ion effect problem as well. You're going to write the dissociation or the breaking up into the ions of these two salts. You're going to write the KSP expression for each of them. You're given the KSP, and you're given the concentration of X here and the concentration of Y here. What you want to do is calculate the concentration of silver ions that would be needed to form a precipitate. And then once you do that, the one that needs less silver ions to form a precipitate is going to be the one that precipitates first. All right, my friends, so while you're finishing that up, I'm going to switch to my document camera here, and then we will look at what we have to do for this one. Oops, that's all right. Here we go. All right, so let's see how we would do this one. So I'm going to start with AGX first. Okay, it breaks up into its ions. So I've got my silver ions and my X ions. I write my KSP expression. Since it's a 1-to-1 ratio, I've got 1 and 1 for my exponents. I know my KSP. I don't know the silver ions to form the precipitate, but I do know that I have 0.10 moles per liter concentration of my X ions. So if I divide both sides by 0.10, that's going to tell me the concentration of silver ions I would need to add to this first solution in order to saturate the solution and start to form a precipitate. So 1.5 times 10 to the minus 11. Now I'm going to do the same thing for AGY. I'm going to break it up into its ions. I'm going to write my KSP expression. I'll substitute in 1.6 times 10 to the minus 9 for KSP. I want to find out what would my silver ion concentration be to start to precipitate Y out of the solution if my concentration of Y is 0.10. So divide both sides by 0.10 gives me X. And X tells me the concentration of silver ions I would need to add in order to saturate the solution and start to form a precipitate. So now I would look at this number here and this number here. Okay, I start out with no silver ions in the solution. I don't have a precipitate. As I increase the silver ion concentration, eventually I get to 1.5 times 10 to the minus 11 for my concentration of silver ions. As soon as I get to that point, I'm going to go above that KSP value, which is going to shift the equilibrium to the left and start to precipitate AX. I would have to add a lot more silver ion before I would saturate this solution and then start to precipitate AGY. Just another kind of KSP problem. Okay, and we did a couple of problems like this, maybe last week or so. Questions? Hopefully it looks familiar. All right, so let's look at another problem. Oop. Okay, good. All right, so the next kind of problem we'll look at is still a KSP problem. This time, it's going to involve a reaction. So we have a solution that contains 0.0020 molar potassium chromate. I should give you the formula for that. I'm not going to write them as names on the test. So potassium chromate is K2CrO4. K2CrO4. We've got 0.0020 molar and 25 milliliters. We're going to mix it with a solution of lead 2 nitrate. And again, I'm not going to give you the names on the test. I'll give you the formula. So lead 2 nitrate is Pb parentheses NO3 2. Pb parentheses NO3 2. And we have 0.000125 molar lead nitrate and 75 milliliters of it. We want to decide, will a precipitate of lead chromate form? So what we need to do is find out what's the concentration of lead ions in this solution. What's the concentration of chromate ions in this solution? Plug them into Q and then compare them to K. If Q is too big, we'll form a precipitate. If Q is too small, we will not. So let's see how you do. If you're not sure what to do, please feel free to ask. I don't want you to just wait until I show you the answer, because I'm not going to be able to do it for you on your test. Okay, so you're going to have to figure out, well, start from here. Since you're looking at lead chromate, okay, write your KSP expression. Okay, so lead ions times chromate ions. Then you're going to have to figure out what the concentration of lead ions are. So take your molarity times your volume, that'll give you the moles. And then divide it by the new volume, that'll give you the molarity of the lead ions. And then do the same thing for the chromate, take the molarity times the volume, that'll give you the moles of the chromate. Divide it by the total volume after we mix the two solutions together, that'll give you the molarity. And then plug that into your Q expression and compare it to K. Hopefully that helps. The total volume is 25 milliliters plus 75 milliliters. You want to decide whether Q is smaller than or larger than K, and what does that mean about forming a precipitate? All right, I'll give you another minute. All right, so I'm going to share my document camera. And let's see how we did. Yeah, I got a couple of, there is a precipitate, and I agree. All right. So you don't necessarily have to write this, but I wrote the reaction up along the top. Here's our potassium chromate, so K2CrO4. And here's our lead nitrate, PbNO32. We're going to produce potassium nitrate and lead chromate, PbCrO4. And we want to decide, will this precipitate? Well, in order to do that, we need to know what the concentration of lead ions are when we mix our two solutions together, and what the concentration of the chromate ions are when we mix them together. So for the lead ions, I took the molarity times the volume, and that gave me the moles of lead ion. I took the moles of the lead ion and divided by the total volume. Now, it was 75 milliliters, and I added 25 milliliters. That means now my new volume is 100 milliliters or 0.1 liters. So my new molarity, that should probably have an 8. Yeah, that should have an 8. I dropped a number. 9.38 times 10 to the minus 5. When we look at the chromate, we're going to do the same kind of thing. So we'll take the molarity times the volume. That'll give us the moles of the chromate. Divided by the total volume, that'll give us the molarity of the chromate. Okay, now once we figure out what the molarity of the chromate is, then we want to calculate Q. So the concentration of the lead ions times the concentration of the chromate ions. There should be an 8 here because I dropped a number. So 9.38 times 10 to the minus 5 times 5.0 times 10 to the minus 4 gives us a Q value of 4.7 times 10 to the minus 8. K is 1.8 times 10 to the minus 14. K tells us what the maximum product of the ions will be before a precipitate forms. Q is bigger than that number. That means there's too much ion in solution than the solution can actually hold. So yeah, there would be a precipitate. I agree. Okay, so let's stop there. What do we want to talk about for that question? And again, there really isn't anything that we're going over now that we haven't done other problems on in previous sessions. We're just kind of reviewing, doing a couple more practice problems to bring it up into maybe our more recent memory so that we're set and ready to go for Monday. Up or down, Kate? Up. Okay, you got it. So it is a little bit confusing to keep track of K, but K is essentially the same thing, just in different scenarios. It's always going to be the concentration of the products over the concentration of the reactants. It just depends on what the specific example is that you're looking at. So in a way it's confusing, in a way it's consistent. So hopefully that helps a little bit. All right, everybody okay with this one? Good. All right, so let's look at one more and then maybe we'll take a couple minute break. Yeah, all right. Actually, let's do all of the stuff that I set up here for the review part of your test, and then we'll take a break and then we'll do some older stuff. All right, so here we have a reaction. We want to identify what's being oxidized and what's being reduced. And then we want to balance that equation. That means you need to assign oxidation numbers. I think what I'll do, as opposed to showing you the answer worked out, I'll go over it with you, because oftentimes once a redox reaction is balanced, it's kind of hard to go back and figure out what you did. So I will do it with you in a couple minutes. Well, let's see if you can do it on your own first. Aaron, you had a question?
Yeah. So I know that the oxidized ones lose electrons, but right here, the part that's losing electrons, CR07, CR207 is being split apart. So it looks like chromium or CR is losing the electrons, so it's the one being oxidized. But what about 07? Like, what about oxygen? Like, is it losing it or is it gaining electrons? Because I can't tell, since one of them started off with more electrons and
Well,
the other
true.
one.
So if you were to look, let's look at the H2O2 first, okay?
Mhm.
Actually, if everybody has it written down, let me just switch to my document camera. All right, so I wrote it out. Okay, hopefully we assigned our oxidation number. So, and this is hydrogen peroxide. It's a little bit unusual. It's going from, well, hydrogen is a +1. Now, oxygen is usually a -2. It's actually a -1 in this one, because this is O2, has a total charge of -2. Each oxygen is -1. Okay, chromium is a +6. Okay, where do we get that from? Well, we know oxygen's a -2. -2 times 7 gives us -14. The sum has to be -2. That must mean chromium is a +12, but there are 2 of them, so each chromium is a +6. Okay, the oxidation numbers are per atom. Okay, not the total that you would have in the molecule or the ion you're looking at. Okay, oxygen over here is a free element, so that would be 0, and chromium is a monatomic ion, so it would be 3+. All right, now, when we look, clearly we can see that chromium is changing. Okay, it's going from a +6 to a +3. Okay, so let me ask you this. If chromium is going from a +6 to a +3, is it being oxidized or reduced?
It's being oxidized.
Numbers going down.
The number of, oh, so it's being reduced.
It's
because
being
it's gaining
reduced.
electrons.
Yeah.
Okay.
Okay. And then, yeah, the oxygen is changing here, but it's also changing here. Okay, so here is going to be what's being oxidized. All right, so let me ask you this. Since the chromium is being reduced, okay, is that going to, actually, that's not even what I want to ask, so never mind. All right, so we want to balance our reaction. So we're going to do our 2½ reactions. Okay, we'll do our reduction. Our oxidation, I probably didn't leave myself much room. So I'm going to write down CR2O7 -2 to CR +3, and then H2O2 to O2. I want to write the charges first, just so I'm consistent. All right, so go through the recipe of how to balance a redox reaction, okay? You want to balance everything except for hydrogen and oxygen first. That applies to the reduction, but not to the oxidation. Balance the oxygens by adding water. Balance the hydrogens by adding hydrogen ions. It is an acidic solution. And then balance charge by adding electrons. And then make sure your electrons gained equal your electrons lost, and then you have your balanced equation. Okay, so I'm going to put a 2 here. So I have my chromiums balanced. I'm going to add 7 waters. So my oxygen is balanced. I'm going to add 17 hydrogen ions. So my hydrogens are balanced. And then think about the charge. This is a +6. I need a +6 on this side. I have a +14 and a -2. That gives me a +12. That means I need to add 6 electrons. And remember, again, that reduction is the gaining of electrons. It makes sense that that's on the reactant side. We're gaining those electrons. We do the same thing with our oxidation. Now, there isn't anything that we need to balance other than oxygen and hydrogen, so the first step doesn't apply. We have 2 oxygens here and 2 oxygens here, so we don't have to add water. That second step doesn't apply. We have 2 hydrogens here. We have to add 2 hydrogen ions here. And then we have a 0 charge here, so we have to add 2 electrons to balance our charge. Here's our electrons gained in our oxidation. Here's our electrons lost in our reduction. Oh, sorry, I did backwards. Here's the electrons that are gained in our reduction. Here's the electrons that are lost in our oxidation, and they're not equal to each other. What would we need to multiply the oxidation half reaction by to get electrons gained to equal electrons lost? What are we going to have to multiply this number by to get it to be equal to this number? 3, agreed. So this becomes a 3, this becomes a 3, this becomes a 6, and this becomes a 6. All right, now, electrons gained in the reduction equals electrons lost in the oxidation. That will always happen. We have 14 electrons, or sorry, 14 hydrogens on the reactant side here, and we have 6 hydrogens on the product side here. We want to write a net number of hydrogens. These 6 hydrogens will cancel out with 6 out of the 14 hydrogens here. That's going to leave us with 8 hydrogens. And then we've got our dichromate plus our hydrogen peroxide on the reactant side. And we're going to yield our chromium ions plus our water, plus I'm running out of room. I can fit it. Our oxygens. Okay, and then we can double check. We've got 8 hydrogens here. And we've got 6 hydrogens here. That gives us 14 hydrogens. We've got 7 times 2, 14 hydrogens. 2 chromiums, 2 chromiums. 7 oxygens here, 6 oxygens here. That gives us 13 oxygens. We've got 7 oxygens here and 6 oxygens here. That gives us 13 oxygens. So the atoms are balanced. We have a +8 and a -2. That gives us a +6 on the reactant side. And we have a +6 on our product side. Okay, so identifying what's being oxidized, what's being reduced, balancing redox reactions, a quick review of that. What do we think? Hopefully, since we've done it for a while, you've done some homework on it, you're like, oh, okay, I can do this now. Sometimes it just takes a little while.
Can you slide the paper up a little bit, please?
Sure, of course. All right, my friends. So let's go back. I think that's all I have for that. Actually, let's just we'll do this problem and then we'll take a break. So this is another, I think that's the last one I have. Yeah, okay. So this is another electrolysis problem. Okay, so we've got a copper ion solution. We want to find out how much copper is going to be plated if we run 10 milliamps for 30 minutes. And you're going to have to take those milliamps and convert them to amps. And you're going to have to convert minutes to seconds, since an amp is a coulomb per second. It needs to be in seconds, not minutes. How many electrons do we have when we're looking at copper ions going to copper atoms? Look at the charge on the copper ions. How many electrons? Going from a +2 to a 0. 2, right, good. Excellent, good. And I agree with the 18 coulombs too. Good, good, Owen. And then if you don't have a periodic table, copper is 63.55 grams per mole. Oh my goodness. You have a very small current for not a whole long time. So it is a very small number we get for the amount of copper that's plated on there, just so you don't get too freaked out when you get a decimal for an answer. Okay, so it should look very familiar to the problems we did at the beginning of the class. Okay, we're going to take the current and multiply it by the time. The only thing we have to do unit wise here is we were given milliamps. We need to convert that to amps. And we're given the time in minutes and we need to convert that to seconds. Okay, and I kind of put brackets around it so we can see this is getting us to amps. And again, an amp is a coulomb per second. This is going to give us seconds. Seconds are going to cancel out, and that's where that comes from. So our charge is 18 coulombs. Okay, we're going to go from charge to moles of electrons. This is Faraday's constant. Then we're going to go from moles of electrons to moles of copper. And it told us that we were looking at a solution of copper 2 ions. So the ratio is 2 to 1. That's where this is coming from. And then we're going from moles of copper to grams of copper. So because it's a really small current for not a whole long period of time, there isn't much copper that actually gets plated out onto that cathode. All right, so we are going to take a break for a couple of minutes, and then we'll do some practice problems on old material that we haven't talked about in a while to kind of bring that back up into our more recent memory. And then we will wrap up our class. So I'll give you about 5 minutes, get up, take a break, do whatever you need to do, and then we'll come back just a little bit before 7:30, let's say. Let me stop sharing that. All right, so let's look at some older material. Okay, and we'll do them. You don't have to do all 3 of these at once. Let's do one at a time, and we'll flip back and forth between here and our document camera. So we did talk about concentrations for solutions in lots of different ways. So in this case, it says the density of an aqueous solution that is 23.4% by mass XY3, whatever that is, doesn't matter. It gave us the molar mass, is 1.13 grams per milliliter. Calculate the molarity. So what you need to do in order to do this problem is define what it means to have a 23.4% by mass solution. Write that down first. And then after you do that, figure out what you need to know in order to calculate the molarity of the solution, and then see if you can figure out what to do. But start with, what does 23.4% mean? Okay, now I'll give you a hint that the 23.4% by mass means there's 23.4 grams of XY3 in every 100 grams of solution. That's where you want to start. 23.4% means 23.4 grams of XY3 in 100 grams of solution, and then figure out what you need to do from there. When you get your molarity, put it in the chat. Excellent, I agree. All right, so I'm gonna switch my camera. Give you another minute to see how you did. Again, this is the important part right here. It's your starting point. If you have 23.4% of XY3 in your solution, it means you've got 23.4 grams of XY3 in 100 grams of solution. You want to calculate the molarity. Well, molarity equals moles of solute over liters of solution. Okay, well, how can we get there? Well, we know the grams of our solute and it gave us the molar mass. We can figure out the moles. We know the mass of the solution. It gave us the density, so we can figure out the milliliters. And then we want to convert that to liters so that we can plug it in and calculate our molarity. So 4.55, I agree. Good. Questions on that? That was a while ago. Good long time. All right. Let's see what we got next. All right, so here's our next question. Calculate the mass in grams of XY2 that can be dissolved in 646.8 milliliters of solution. It gives us what the molar mass is and it tells us what the KSP is. So this is a KSP problem. Okay, take XY2 and break it up into its ions, write the KSP expression, and then figure out what you can do from there. And you're going to have to add on to this because once you calculate what the molar solubility is, you're going to have to use that, the molarity, and the volume to figure out the grams of the solute that was there. got something a little different. Let's look and see. Maybe you can catch my error. All right, so we've got XY2 breaks up into X ions. The charge on X is a +2. And Y minus ions, okay, the charge from the Y is -1. And to balance it, we need a 2. So KSP equals the concentration of X ions times concentration of Y ions squared. It told us the KSP was 4 times 10 to the -9. That equals X times 2X squared, which gives us 4X cubed. Divide by 4, take the cubed roots, and the concentration is 1 times 10 to the -3 molar. Okay, now we're adding on the solution part onto this in that we know that molarity equals moles per liter. We can calculate the moles by multiplying both sides by the volume. So the molarity times the volume gives us the moles of the KX2. Multiply that by the molar mass, and that gives us our grams. Okay, do we agree with that? Because there were a couple of different answers in the chat. Did I do something wrong? Do we agree with that number? Okay, good. If you didn't get that number, do you see what was wrong? All righty, good, excellent. All right, so let's try another one. All right, now we're going to use solutions and apply it to a freezing point depression problem. That's a molality type of a question. See if we remember how to do that. Remember what happens to the freezing point when you add a solute? Does it go up or does it go down? That'll help you to decide whether you're going to add your change in temperature or subtract your change in temperature. Okay, when you get your new freezing point, put it into the chat so that I know A, that you're done, and B, that we have some consensus in the answer. All right, remember that when you add a solute to a solvent, it increases the boiling point, but it decreases the freezing point depression. So when you calculate delta T, you're going to be subtracting it from your temperature. Don't add it to your temperature. All right, so let's see how we did. All right, so this is a problem that deals with molality. Another way of talking about the concentration of a solution, it's the moles of solute per kilogram of solvent. We were given the grams of the solute and the molar mass, so we can figure out the moles of the solute. If we take the moles of the solute and divide it by the kilograms of the solvent, we can figure out the molality of the solution. The freezing point is going to change by a quantity that's equal to the product of the freezing point depression constant times the molality of the solution. The larger the concentration, the bigger the temperature change, and vice versa. So we're given the freezing point depression constant is 2.19 degrees Celsius per molal. The molality we calculated to be 2.38 molal. So our temperature change is 5.21. But again, freezing point depression means the freezing point is going to go down. It's going to go down by 5.21. So 3.1 minus 5.21 is going to give us negative 1.31. Okay, we're just applying a concentration type of a problem. How'd we do? Remember, freezing point depression, boiling point elevation. If we add a solute, the boiling point goes up because the vapor pressure goes down. And if we add a solute, the freezing point goes down because the vapor pressure goes down. That was a while ago too. All right, so let's look at another one. All right, so now let's look at an integrated rate law problem. This was a while ago. An integrated rate law problem. It tells us it's a first order reaction. Okay, it has to tell us that. It tells us that the rate constant K is 3.31 times 10 to the minus 3 reciprocal minutes. If the initial concentration of reactant is 0.545, that concentration is going to go down as the reaction proceeds. We want to find out what the concentration is after 4.6 hours. Now notice that K is given to us in reciprocal minutes and the time is given to us in hours. So we have to adjust the units so they match up. And for first order reactions, the time and the natural log of the concentration are inversely proportional, or sorry, are directly proportional. So the natural log of A after a given amount of time equals negative KT plus the natural log of A at the initial concentration. So ln of A equals negative KT plus the natural log of the initial concentration. And maybe this will be a good, and I'm going to share this with you so you have it at the end of class. There is an equation sheet on the final exam. Okay, I just heard a whole bunch of collective sighs of relief. That's good. There is an equation sheet on the final exam. I'll share it with you so that you can look at it in advance. But it will have all the different types of equations that you need. Yeah, see, I knew I felt all that collective sigh of relief. So that should help you, hopefully. Good. So we have some consensus on the answer. Excellent. All right, so let's see how we did. So when we talk about a first order integrated rate law, we're looking at the natural log of the concentration versus time, giving us a linear relationship. So our equation, that y equals mx plus b equation, the natural log of the concentration after a period of time will equal negative kt. K is the constant we were given, t is the time, plus the natural log of the initial concentration. So for K, we would plug in 3.31 times 10 to the minus 3 reciprocal minutes. For time, we would plug in 4.6 hours, but since the units have to be consistent, I converted hours to minutes by multiplying by 60. And then we're going to add the natural log of 0.545 to that. And we get negative 1.521 equals the natural log of A after this time period. Well, the opposite, the reciprocal, the opposite of the natural log is e to the x. Okay, so find the natural log button on your calculator, and the second function of it is e to the x. So you would take that second function, e to the negative 1.521, and you get 2.18. Okay, so that means that you started out with 0.545 moles per liter of whatever this is. It reacted for 4.6 hours, and now we have 0.218 as our new molarity. And again, I'm going to give you an equation sheet on the final exam. And you'll have your integrated rate law equations in that set of equations. All right, so let's try this one. Okay, this has two parts to it. Okay, we're given delta H, we're given the enthalpy. We're given delta S, or we're given the entropy from that, we can calculate the free energy. We can calculate delta G. Okay, now the units don't match up for delta H and delta S. You're going to have to do something to your units. Once you calculate delta G, you can use that value to calculate the equilibrium value, the Kc value. So you're going to use delta G equals delta H minus T delta S in your first step. Okay, make sure your units for delta H and delta S match up, and make sure that your temperature is in Kelvin and it was given to you in Celsius. Okay, just some things to kind of be aware of when you're doing your problem. Think about what your delta G value means. Aaron, do we need delta what? Not delta A. Do you want delta S? You want to convert delta S?
Oh, yeah, I
Yep,
meant delta S.
yep,
That was a
yep.
typo.
Yep, you want to, it doesn't really matter whether you convert one to kilojoules. Actually, probably it would be more helpful if you converted them both to joules, but it doesn't matter. They just have to be the same.
Okay.
Okay.
Yep. Thank you.
Actually, for the second part of the problem, it might be helpful if it was in joules anyway, but
Oh, okay.
So-
So I'll just convert delta H then.
yep. You just
Okay.
have to convert it twice then if you didn't. So when you do your conversion from delta G to K, K equals E to the negative delta G over RT. And R is 8.31 joules per mole Kelvin. So that means your delta G is going to have to be in joules anyway. R is 8.31 joules per mole Kelvin in your equation. Okay, so your equation, it's delta. Okay, not theta, delta. And it's K equals E to the negative delta G over RT. Okay, K equals E to the negative delta G over RT. You're welcome. All right, so I got for delta G negative 195 kilojoules per mole. So hold on, let me put down the answer here and then I'll go back. So you should have, let's see, if you did the joules, 0.091 plus 520. Make sure you converted Celsius to Kelvin. 524 times times 198, negative 198.6. Oh, wait, maybe that is right. Hold on. Maybe I did it wrong. No. All right, so let's see how we did. All right, so let's look at the first part. If we know enthalpy, it's exothermic. And we know entropy, it's becoming less disordered or more ordered. Okay, I converted them to kilojoules. I probably should have converted them to joules because then I had to convert them here anyway. But I just divided the joules by 1,000 to get my kilojoules. So I got negative 195 kilojoules per mole or negative 0.195 joules per mole. Okay, to relate K to delta G, K equals E to the negative delta G over RT. So my R value is 8.31 joules per mole Kelvin. That means I need to use my delta G value in terms of joules. Okay, so E to the negative 0.195 over 8.31 over 528.
The top equation for delta G wouldn't, in the second part, you did not negative 91 plus, wouldn't it stay minus?
Say that again, where?
For the top equation for delta G,
Uh-huh.
and you have negative 91
Oh, this should be a
kilojoules.
minus. Oh, geez, where'd that come from? That's gonna change our answers then, isn't it?
I have 13.07 kilojoules per mole.
So maybe that's what it was. Somebody else said that too. 13 point what?
Negative 13.07
Okay, so
kilojoules per mole.
13.1, we'll leave that as. So this becomes 1, 2, 3. How about that? Is that better?
I meant mean positive. Sorry.
Oh, you're right. It is.
Positive.
You're right. It is positive. I agree.
Positive, yeah.
All right. That's going to change this number. I'm still getting the same answer. Yeah, I'm still getting the same answer. We agree with that? Oh, Jesus.
Now that's
Wow. You are right. So that's 1, 3.
0.66.4.
Yeah.
Oh.
My God, what is up with me?
Okay, I was really confused because I was like, that looks very similar to what I got, but
Yup,
off by a couple of zeros.
it is.
Could you maybe scroll up? Because I did everything on calculator, but it's nice to see it like written out.
Better?
Yeah, thank you. Okay, good. That's reassuring.
So how about 0.049? Does that work better?
Need to put this back into the calculator.
I'm doing too many things at one time. 8.51. 5.24. Yep, that's what I got. Thank you for catching all my errors. Got too many things on my mind.
Hmm.
All right, my friends. It is 8 o'clock. So let's stop